How can advisors visit dozens of post-training establishment without losing time or their sanity? This study uses traveling salesman problem or TSP to map the most efficient routes for supervising student interns. Stay tuned for how we can make supervision smarter and faster. According to Ottman et al. In 2022, education is a fundamental human right that empowers individuals and transforms societies. At Bulacan State University, on-the-job training enables students to gain valuable skills in professional environments. However, for faculty supervisors, visiting numerous host-training establishments creates significant logistical challenges, particularly when managing limited time and resources. Supervisors must navigate up to 37 HTE, leading to a stressful travel. This study addresses the issue by applying traveling salesman problem, or TSP, an optimization approach that identifies the most efficient one-way travel route. Using graph theory, HTE are modeled as points and their distances as weighted edges, producing a structured route to minimize travel time and cost.
This study uses the traveling salesman problem or TSP to help instructors plan the most efficient route when visiting students in various internship sites. By minimizing travel time, cost, and energy, TSP allows instructors to focus more on supporting and monitoring students. This method isn't just for education, it is widely used in logistics, manufacturing, and service industries to improve travel efficiency and reduce expenses. Through this study, we aim to show how TSP can make travel smarter, more practical, and cost-effective for professionals who regularly move from place to place.
The general objective of this study is to determine the most efficient travel path for internship visits. To achieve this, we have identified the following specific objectives. First is to examine the current travel routes by representing company locations and travel paths as vertices and edges within a graphical representation. Second is to develop the most optimal route by applying the traveling salesman problem that would reduce time and distance traveled and can be reused in future internship visits. To improve the overall workflow of internship advisors by minimizing logistic burdens associated with visiting multiple sites. Prior to the main discussion, it's important to understand the foundational concepts behind our study, so we introduce the base of graph theory. Graph theory is a field of mathematics that deals with graphs, structures made up of vertices representing points or locations, and edges representing connections or paths between them. This concept was introduced by Leonard Euler in 1736 through the famous Seven Bridges of Königsberg problem. Graph theory is widely applied in solving real-world problems, especially in logistic, network optimization, and route planning. In our case, each internship company is modeled as a vertex and the routes between them as weighted edges.
A graph is a structure made up of vertices and edges. Think of it as a way to represent connections between things, like cities on a map, people on social media, or computers in a network. Vertices or nodes are the individual points. Each one represents an object. In a graph, every vertex is unique. Depending on the context, a vertex could mean a city, a person, or even a computer. Edges are the lines that connect those vertices. They show the relationships between the objects. In undirected graphs, edges go both ways. In directed graphs, also called digraphs, they point one way. Graphs can also have loops, where a vertex connects to itself, or multiple edges between the same pair of vertices, like in a multigraph. Some graphs are weighted, meaning the edges carry extra info, like distance, cost, or time. In real life, graph shows up everywhere. In social networks, vertices are people, and edges are friendships. To sum it up, a graph is equals to vertices plus edges. Together, they help us visualize and solve complex problems. Let's talk about weighted graphs, a powerful concept in graph theory that helps us solve real-world problems like finding the shortest path or most efficient route. In a weighted graph, each edge has a numerical value, called a weight. This weight can represent distance, time, cost, or strength of connection. For example, think of cities connected by roads. The numbers could represent kilometers or travel time. Weighted graphs are used in areas like transportation planning, internet routing, or social networking, and even project scheduling. They help optimize paths, reduce cost, and improve efficiency. In our case, we're using a weighted graph based on distance to help internship advisors find the shortest and most efficient route when visiting interns in their companies in Pampanga, Bulacan, and Metro Manila. So next time you're trying to find the best route, remember, a weighted graph might just be behind the solution.
The traveling salesman problem or TSP is a classic problem in graph theory. It involves finding the shortest possible route that visits each location exactly once and returns to the starting point. In this study, the TSP is applied to optimize the routes taken by internship advisors. These advisors are responsible for visiting multiple internship companies across Pampanga, Bulacan, and Metro Manila, ensuring each company is visited once before returning to their starting point.
For the main discussion in the study, we treated each internship company as a node or point in a graph, and the rows connecting them as edges. The distance between companies measured in meters serves as the weight of each edge. All routes begin at Bulacan State University, which we use as the starting point for consistency across all graphs. For our data, we compile a list of companies that previously accepted third-year BS Mathematics students for internship. Most of this information came from the official Facebook page of the College of Science Student Internship Program, which regularly posts updates and records of internship placement. During the data gathering, we found that two companies had incomplete location details and could not be traced on Google Maps. Therefore, we had to exclude them from the study, leaving us with a total of 35 companies for the analysis. To make our analysis clearer and more organized, we grouped these companies based on their location into three main areas: the Bulacan-Pampanga area, which include 12 companies, the South Bulacan area with 13 companies, and Metro Manila area, which also has 12 companies. In all three groups, Bulacan State University serves as the starting point for calculating travel routes. We then used Google Maps to carefully locate and mark each company. This allowed us to accurately measure the travel distance between them, which we use as the edge weights in our graph. These distances are essential for building an efficient and realistic routing model. Following this, we mark the map to visualize the location of the company. Figure 1 shows the Bulacan-Pampanga map, and the nodes or companies included in this area. We also have Figure 2, which is the South Bulacan map, and Figure 3, which shows the Metro Manila map. Then in Figure 4, we show the converted graphs with clearer edge connections between the companies for Bulacan-Pampanga area. Figure 5, which shows the South Bulacan area, and Figure 6 that shows Metro Manila area. It is important to note that these graphs are not fully connected, meaning that every company is directly linked to each other. In some cases, a route between two companies required passing through a third one. For example, going from company A to company C might require passing through company B. In such cases, the total travel distance is calculated by adding the distances from A to B and B to C. Once the basic structure was in place, we added the actual distance values to the edges, creating what we call weighted graph. And it is shown in figures 7, 8, and 9. And these graphs now represents the true travel distance between companies and are ready to be used for finding the shortest and most efficient route using TSP. With these graphs fully prepared, we are now ready to apply the traveling salesman problem to determine the optimal visiting routes for each area.
In our study, we tackled the traveling salesman problem or TSP by using SageMath version 10.4. SageMath can handle a wide range of mathematical computations, including graph theory problems. One of the strengths of SageMath is that it has a built-in function for solving the TSP. This function is called traveling salesman problem. Before we use it, we first set up the graphs for each region by plotting the locations of the HTEs. These graphs were shown earlier in the presentation. Once the graphs were defined, we run the function to find the shortest possible route that visits each HTE exactly once and returns to the starting point, which is the Bulacan State University. Let's now look into the results. For the Bulacan-Pampanga area, the optimal path to cover all 13 HTEs results to a total travel distance of 136,640 meters. In the South Bulacan area, the function also covered 13 HTEs, with the optimal route totaling to 138,700 meters. Lastly, for the Metro Manila area, where there are 12 HTEs, the computed shortest path had a total length of 161,200 meters. These results show how graph theory and optimization algorithms can help solve real-life problems, like planning the most efficient routes for educational visits.
This study used the traveling salesman problem or TSP to help boost professors plan better routes when visiting internship sites. With 35 companies grouped into three areas, the researchers used Google Maps and SageMath to calculate the most efficient travel path. The optimized total distances were 136,640 meters for Bulacan, Pampanga, 138,700 for South Bulacan, and 161,200 for Metro Manila. Since the graph use was undirected, professors can take the route in either direction without affecting the distance. This flexibility helps them adjust based on traffic or convenience. The study showed that TSP can make internship monitoring easier, save time and resources, and even improve how professors support students. It also proves TSP's usefulness in other fields like logistics, delivery,